So hello, I am Alberto Planas. Thank you all to be here. And today is a very important day for me because this is the day that I'm going to present a work of at least two teams related with full disk encryption and how we can start using a new model of full disk encryption in openSUSE since at least since the beginning of the year. So let me start with an introduction. I always start with this slide that is the motivation, why we want and what we expect about full disk encryption. Basically, it's about data protection and data authentication. Data protection is what all we expect. That is, if our device is storage or so our device is lost or or is stolen, no one can access to the data that is stored there. But it's also about data authentication. That is, if we have a side channel attack and the data has been changed, we need to have the chance to be detected, this change. For us, this is very important because we have microS, and rollback is a property of microS. So if we have a non-authorized rollback, we should be detecting that in a full disk encryption situation. But it's not a silver bullet, so it's not going to protect about everything, more explicitly about a local exploit. If we have a local exploit and someone becomes root, is this game over for us? For that, we have different technologies like IMA and EVN or remote attestation, but this talk is not about that. But it's also about another secondary motivation for openSUSE is important. It's about looking for a reference implementation. So in Windows or macOS, we have bootloaders or file vault, that reference implementation with good things, bad things, but it's a very well-known implementation with very clear expectation about how they are going to work and what are protecting us. And for us, systemd is proposing a set of tools that we can use to build this kind of reference implementation in a way that is aligned with our properties. openSUSE is kind of different. We are using Btrfs, a snapshot. So we should be sure that whatever we are using is going to be compatible with our characteristic of features. But also it's a good opportunity to join an open project, to start participating in the design, to communicate our intentions, and share the security reviews that typically is not an easy thing to do. Julie mentioned that full disk encryption is not something new in openSUSE. We have the traditional bootloader-based full disk encryption, where it's grab, the one that is first asking the password to the user, is unlocking the encrypted device, and from there, read the configuration file, the kernel, and initrd, and start the boot process. The bad thing is that most of us that we use this kind of configuration is kind of bad or misconfigured, because initrd, the moment that initrd needs to access to the Lux device or the encrypted device, is going to ask again for the password, and we are going to have to enter the password 2 times. This is something very typical in openSUSE, and so we should do better, no? The good thing is that it's supported by us since a long time ago, and over the time they improve it. For example, Grab today is supporting TPM2 to avoid entering the password. It's an automatic way to enter in the password, asserting the health of the system via some components, some plugins that are known as key protector. So the architecture in this old model or current model is very similar to that. We have the grab in the FEI case. We have grab in the FAT in a FAT partition that is the ESP, and the rest of the system is in a Btrfs file system. The most important part, the root file system, is going to be living in the encrypted side, but also the /boot. /boot is where the kernel and the initrd reside. This is a typical situation where grab is going to ask the password, and the initrd is going to ask the password a second time. We documented over the time. We documented how to avoid the second asking the password for a second time. Basically, consists of adding a key in some place in etc, configuring Dracut in a way that initrd is going to include this password. So via documentation, we can resolve this issue. And lately, Grab have a way to injecting the password in the initrd one that is entered. So it's a situation that evolves over the time. With TPM, so we can use the TPM with grab2 using, in that case, we can move from lux1 to lux2. And using the injection, we can avoid the introduction of the password, basically because we're in a situation we don't know the password that is stored in the TPM. But this talk is about doing it better. So the basic proposal is that the bootloader should be something very small, very simplistic, and the responsibility of the bootloader should be booting the system and delivering the load to the kernel initRD to do the rest of the stuff. And in this case, doing the stuff related with full disk encryption. This proposal is based on two different pillars. One is the bootloader specification. This is not a must, but it's a property that is going to simplify massively the work. And the second pillar is the systemd tools related with full disk encryption. It's a set of tooling that are related with setting the encrypted device and the enrolling of the device and the managing all the details about full disk encryption. This decision of this design have nice properties. One is the speed is going to be much better, essentially because we are going to access to better software with optimized encrypted libraries. It's going to be more modular. That means that we can use a subset of the tooling, and it's going to be magnitudes of order more easy to debug. So it's very easy to introspect and replicate issues. The bootloader is kind of a black box, and in this case, the black box is not there anymore. A side effect of that is that we are going, from the beginning, we are going to have multiple authentication mechanisms. So we can have certificate, password, TPM, TPM plus PIN, FIDO keys, and others that we can implement ourselves. The difference in that case is that the kernel and the initRDs are going to be stored in the clean site, in the ESP. So the architecture is kind of similar, but the difference is that the bootloader and the kernel and the initRD are going both to be living in the ESP, in the FAT32 partition of the ESP. But the other partitions are, so root file system, etc, and var are going to be living in this case, a full lux2 device. In that sense, the proposal is that UEFI is going to start the boot process. The bootloader is going to do very little. Basically, it's going to read a configuration file that is going to contain a description or where to find the kernel, the initRD, and the kernel command line for this booting process. And the initRD is the one that is going to decide if the Lux device can be open or not based off the password that the user entered or the assert of the TPM that we have in our system. That opened the door to have a full measure boot process and some properties that we can take advantage of that. As commented, in this new architecture, we are not going to depend anymore on having one single bootloader. So we can have, in the older architecture, we are going to have a grab2 FAI. But in this new architecture, we can have systemd boot, but also we can have grab2 BLS, that is a version of grab2 that is packaged one single binary that is deployed in the ESP, very similar to systemd boot, that contains all the assets, all the theme and configuration files in a single file that we can move and install in the same way that systemd boot, but also understand the snippets, the configuration file from the bootloader specification. Basically, the bootloader specification is a document that describes how those boot entries are going to be described, and they talk about type 1 or type 2. Type 2 is the famous UKI single file that contains the kernel, the initRD, and the kernel command line in a single PI executable. But we are going to, in that case, we are talking about the old model that is type 1, when you have a text file that contains the place of the kernel and the initRD. The good thing about this model is that now we can use TPM2 in the full fashion. So I think that TPM are not new anymore. We know how they are used typically, but basically they are sometimes virtual because it's not a real hardware. Sometimes it's a real chip. It's a virtual crypto device that offers a very rich and complex API to the developer. We are going to use only 3 components for this model. We are going to use 3 components for full disk encryption. One is the measure boot, that is the specification explained that measure boot is at the process where, since the beginning of the bootloader, since the beginning of the UEFI, when the firmware executes, each component, each state of the boot process is going to load the next step, and is going to measure, calculate a hash of the code and data of this stage, and do an extension, that is a cryptographic operation, in some internal register that is inside the TPM. Those registers are known as platform configuration register of PCR. There are like 24 of them, and they are of the size of a hash algorithm. So we have one size for hash 1, one size for hash 256. So we have different sizes, and they are going to store the cryptographic operation of the hash of the current value of the PCR and the new hash calculate for the new blob that has been loaded, and the hash resulting of appending both hashes is going to replace the old value. The good thing is that there is no reverse operation for that, and it's very easy to calculate forward. So that allows us to separate if we can calculate, if we are the owner of the bootloader, the kernel, and the initrd, we are going to be able to calculate the final values of those PCR. And this is going to allow us to separate the good state, so the state that for sure are loading the expected and the correct kernel and initrd, from the bad states, that maybe the initrd is not the one that we expected, or maybe something changed in the firmware, maybe some configuration has been injected without our permission, so we can separate the good state from the bad ones. So the other operation that TPM is going to provide us is the sealing. That is, we can encrypt passwords, we can encrypt some secrets based on policies that are going to condition the unsealing based on some PCR value. So that means that we are going to encrypt the password, but only can be decrypted inside this TPM, so not using a different machine, if the PCR values are this and this and this that we calculate beforehand. The last component that is not a property of the TPM, is a property of the host, is the event log. Because the cryptographic operation inside the TPM is completely opaque, so at the end when we are going to have is a list of values of PCR, but we don't really know why they are reaching this value, is the event log that contains a lot of entries, each for each of one per extension that has been done in the TPM. So if we have the PCR number 2, for example, and is having 3 extensions, those 3 extensions are going to be described in the event log, and we can query those extensions, and we can validate that this information is correct. In the low level, systemd is providing tools like systemd decrypt setup, that is the component that is going to open the LUKS device based on the policy or the authentication method that we are requiring. Can be the password, but can be the FIDO key, or can be the TPM. We have a systemd decrypt enroll, that is a tooling that is going to associate the LUKS2 device with the security token or device that we are using for the enrollment. We have tooling to calculate the new policies that are going to be applied. So it's the kind of tool that is going to generate, based on some metadata that we are going to provide, is going to generate the policy that applied to the TPM is going to seal or unseal the password that is going to open the LUKS2 device. And there are more tooling for encrypting device. This is going to be very, very useful for image-based configuration. And one component that we are going to need to copy from the ESP into the on-memory initrd, some metadata that we need to deliver to keep setup in order to open the device. And finally, we have this sdbootutil tool that is going to orchestrate all the proper calls to those tools in the proper order that are going to provide features or are going to provide utilities for bootloader specifications, so to support the bootloader specification in Tumbleweed on macOS and configure the full disk encryption in openSUSE. So that means that there are going to be a set of workflows that are going to be different from the traditional ones. In some sense, they are going to be more natural, more the one that we expect, but in sometimes are going to be different. For example, one workflow that we are going to need, we need to define is the enrollment. So if we have a device, an encrypted device, how we can associate the encrypted device with the security token. So sdbootutil is providing an API, is providing an interface to different tools like JAS or Disk Encryption tool, Combustion or use modules in order to send in a way that is secure based on KeyCTL or systemd credentials, secret password that the user is going to define, and is going to make the association between the TPM of those passwords with the different Lux device that we have in our system. Another workflow that is going to change is the boot process. So if we are using systemd, systemd setup, and BLS, and the bootloader specification, that is going to be, the boot process is going to be different from the one that we have today. Basically, once the bootloader have access to the ESP partition, it's going to load the bootloader entries and it's going to present a menu to the user to select the bootloader entry that want to load. And depending on the boot entry that is selected, a different kernel, an initrd or a snapshot is going to be selected. Inside the initrd, the Dragwood PCR signature is going to load from the ESP this metadata that is going to be required by systemd setup to open the device, maybe without asking to the user any password, if the TPM assessment is successful. And then there are two other services that we are going to discuss later for adding extra security before the switch root happens. The last and most important workflow that changes is the update process. So we have now a mechanism that allow us to make predictions, so make expectation about the state of the system after the boot. But if you don't change anything in your system, nothing needs to be recalculated. But with ZipperDAT, there is the chance that the bootloader is going to be updated, or the kernel is going to be changed, or maybe the initrd need to be recreated. That means that we need to inject somehow, from one side, we need to do the operation related with the bootloader specification. That means if a new kernel is installed, we need to create an entry for this kernel. If a new snapshot has been created, we need to reuse one of the kernels that we have in our system, now pointing to the new snapshot. So we need some place to hook the proper call to sdbootutil to update all the bootloader specification thingy. But also some of those changes are going to change the predictions, and we need to use these same hooks to update the new prediction for the next boot. I think that with that, we have a basic overview of the architecture, and we can start talking about how to use the sdbootutil. As commented, sdbootutil is merging two different kind of tasks. One related with bootloader specification management, basically creating boot entries, installing the bootloader or updating the bootloader, updating or removing the kernel, configuring a snapshot and the kernel command line. Another important task is managing the ESP free space. The ESP is now a FAT32 partition, and it's expected that all the kernel and initrd that are not small files are going to be living there. And you need to be very careful not to fill the space that is available, because in that case, an update of a new kernel is going to fail and your system cannot be booted. So you need to be smart and proactive in order to manage the free space. And because we are now supporting more than one bootloader that support the bootloader specification, and grab2 BLS is supporting a partial implementation of the BLS, we need some kind of tooling that soften the mismatch that happen between these two bootloaders. So operations that usually are delivered to bootloader are now executed by sdbootutil. But also all the tooling for this encryption management, like the one that we saw, so enrollment of a subset of the disk, delivering secrets in a proper way, managing authentication methods. So we need a way to specify, okay, this device is going to be checked by TPM, but this other device is going to be checked by FIDO2. But also generating policies. We have two kinds of policies that we are supporting. One is the NB index one, that is the cool one, the modern one. Most of us, we can use that if we have a modern laptop, but if we laptop have an old TPM, maybe we can use this tooling, and we need to fall back to a different tool that is PCR Oracle that is going to use the other kind of prediction. So in order to make this transparent somehow, sdbootutil is going to provide this feature. Another aspect, I mean, there are more tasks about full disk encryption, is event alignment. That is a fancy way of saying that we want to guarantee that all the PCR that we expect to measure are going to be measured for the next boot, to guarantee that we have the most coverage of security properties in our system most of the time. There are some concepts that sdbootutil is going to introduce. For example, I mean, sdbootutil is a bit opinionated, and basically what we decide to do is that by default it's going to enroll, or it's going to make change all the encrypted device in your setup. That is usually the case, but maybe not for you. If it's not for you, we are going to provide some parameters and command lines that are going to select a subset of those devices, but you can also ignore or make the system deboot is going to ignore this device if you add in encrypt tab one tag that is sdbootutil ignore. So this device is not going to be managed by sdbootutil anymore. The same for PCR. We decide, I mean, sdbootutil is going to decide, depending of the bootloader that you are using, if you are inside a VM or not, is going to decide the coverage of the PCR that are going to be selected. Some of them doesn't make much sense. So for example, measuring the configuration of the firmware, the data. In certain situations, yes, it's something that you need to do, but most of the time, no. Maybe you want to change something, maybe the time, or maybe you want to change the boot ordering or something like that. And for you, it's kind of okay, but sometimes it's not okay. So the PCR are going to be selected by sdbootutil automatically, but you can change the selection of PCR, editing some file or using some parameters during the enrollment. Another concept that comes from systemd is the concept of recovery key and recovery pin. sdbootutil is making an effort of merging two concepts because sometimes they are kind of similar, but they are different, and we need to be aware of that. Recovery key is a random password that optionally can be enrolled in one of our disks. This makes sense if we want to make an installation unattended, completely unattended. So instead of waiting for entering a password, sdbootutil and systemd are going to generate a random with high entropy key, and it's going to show you at the end of the installation a QR code that you can copy that contains the recovery key, that is the random looks 2K that you can enter in case that something goes wrong. It's like a normal password. But the other concept is the recovery pin. The recovery pin is kind of a technical concept that is required. Basically, is that inside the TPM with NB index policies, inside the TPM, we are going to store the blob that contains the seal key. This has some advantage. Basically, that means that if we make an enrollment or we update this key, we don't need to change any other device. So it's like a process that only happens inside the TPM. We don't need to access to any other device to update the policy. But the problem is that if we are storing that in the TPM, we need some kind of mechanism to protecting this information. For that, we use a secondary password, another very similar to the recovery key, so a high entropy random key, that is also stored in the TPM, that can be open automatically if we are in a situation that is well known for the system, so we are in a healthy situation, and can be used to change the policy. But if we are in a situation that is not secure anymore, for example, we make a change in the kernel, or we enter with a different command line, this password cannot be accessed anymore. But in the situation, we want to update the policy following the new configuration in our system. So for that, we have the recovery pin, that is again a password that we need to enter to make the change inside the TPM. sdbootutil, as commented, is going to make an effort to make these two concepts as a single one. So the same key that is in the recovery key is also going to be the recovery pin, but you can always separate both. So if I want to use this new model today, what I need to do? I mean, not much today, because you can use just that is, in my opinion, a very high and important milestone. It's implemented in Just in a way that we hope that a Gamma can use, because there is a big chunk of code that is shared. And we are working on some bugs, but you can start using that in MicroS and in Tumbleweed. Basically, today you can use to the expert partitioner. And when you have this kind of view, you can select to encrypt one device. And in the encryption of the device, now you have one new encryption method, that is the systemd-based full disk encryption. And in this case, it's going to ask you for the authentication, that you can use TPM, FIDO, TPM plus PIN. And in that case, it's recommended to use Argon2 as a default key derivation function. That is it's an option that we don't have in the old bootloader model, but we have now in the user space full disk encryption, and it's going to secure you the user provide password. So it's a good thing to have. And then you can encrypt one or more partition. In this example, we encrypted the root file system, but we also encrypted swap. There is no problem. You can split more and create an etc or a bar partition, and you can encrypt also those using the same mechanism or different one, and it's going to work. At the end, we need to be sure that some bootloaders some BLS bootloader is going to be selected. In Tumbleweed, the default today is grab BLS, and in MicroS is systemd-boot. So making sure that everything is in place is going to work. But we can do that manually. If we have a looks to device, we can do the enrollment manually using sdbootutil. So we can use sdbootutil enroll, specifying the method, and in this case, specifying that we want to enter the recovery pin. So we need to remember, if something goes wrong, the pin that is going to be asked when we are going to update the policy if we are in a situation that is not a healthy state. As commented, we can select a subset of the device using the device parameter, a subset of the PCR, or extending that for a specific call. And we can do an enrollment. So if we don't specify the devices, all the devices that are encrypted and are not ignored are going to be added or removed from the authentication token. If something goes wrong during the enrollment, my recommendation is always checking if the enrollment has happened, because sometimes the error is happening after the enrollment, maybe during update prediction stage or something later. So with systemd enroll, we are going to list the amount of key slot that we have in our system, so we can see if we have a TPM key slot or not. But the good method that we need to use to report a bug if something goes wrong or ask question is //bb, because this is going to open a debug mode that is going to present more information from sdbootutil, but also from the systemd tooling that are used. So it's going to enable the debug output, and it's going to give more information to understand what is happening. In some situation, when the bug is kind of hidden, or when the bug output is not enough, it's recommended to use bash -x to have very detailed information. That means that it's going to be super transparent what is happening inside there, with the problem that some passwords are going to be printed, so this information is only for you, don't share that. But it's going to explain exactly what is happening there, and you can report exactly what did go wrong. Today, I mean, this is kind of new. We are going to have two kind of predictions. One is the TPM policy. that is the one that is going to live inside the TPM, the one that is going to open the Lux device without asking password. But recently we are providing a secondary prediction for PCR15 that we are going to see that later, but it's the one that is going to protect us to raw device. That is kind of attack that was documented some months ago, and we have the solution here. Both predictions are going to be done, but only the TPM2 one is going to be done by default. So every time that you call sdbootutil update predictions, only the TPM2 policy is going to be updated. The reason is that to calculate the PCR15 prediction, the password from one of the Lux2 devices is going to be asked. This is because the volume key is going to be read, and you need to have permission to read that. We can work on that, so there is a way of not asking the password, but for today, I think that this is a good idea. And actually, PCR15 should not change over the life cycle of your system. So in the case that you want to update PCR15 prediction, you can use / measure PCR to force the calculation of a new prediction for PCR15. If something goes wrong, so if update prediction fails, what the user is going to face is that during the boot process, the Lux2 password is going to be asked if you enroll it at Lux2 password. In the case of Jazz, it's going to be the default, but the user has always the opportunity to drop, to unenroll these key slots from our devices. If we don't have a Lux2 password and we don't have a recovery key and we only have a TPM, there is no password to ask and we lost the data. So that's why the recovery key and the password makes sense to have. I mean, technically we can have a secondary authentication method using FIDO2 key that is also working. So yeah, in that case, no password need to be known. If system deboot fails, we have a tool that we are going to describe later, that's PCR log, that is going to help us massively in debugging why it's asking the password. Basically, sometimes it's a bug in the system, but sometimes it's something that we are not taking account today. We are working to take account that, but not today. For example, firmware updates. So firmware updates, sometimes injecting an FAI module that is going to be loaded, and sometimes sdbootutil is not going to be aware that this module is going to be loaded, and this is going to change the predictions, and that means that it's going to invalidate the measure boot assertions, and the TPM is going to refuse the unencrypting the password, and you need to enter the password. So if you have a firmware update operation recently, maybe you need to enter the password and calculate the new hash for the prediction. But sometimes you are going to face a real issue. So you need to be aware if I didn't make any change, and I don't think that there is any bug in sdbootutil. If the system is asking you the password, or maybe something happened, and you need to act accordingly to that. If the other kind of prediction, PCR15, fails, what is going to happen is that the system is going to refuse the switch root. It's going to halt the system, and it's going to show you a message how to avoid the halt and how to make the recalculation, but it's not going to make the switch root, and the boot process is going to be stopped. As commented, PCR log is going to be the tool to understand why it's asking the password. And if the predictions fail and it's obvious that the problem is a bug in the system, again, /BB is going to give you the point where the complaint is happening. PCR log is a systemd tool that is going to show us two tables, very long and large table, but it's going to do a full analysis of the the firmware and the user event log. So it's going to explain each extension in our system, the reason of this extension, and the value and the evolution of the different PCR. So basically, we are going to have some metadata that is going to explain, okay, this PCR number 5 has been extended, this PCR has an extension because of this reason, and the hash value is going to be this one. This information is very useful for us because we can validate this hash with the information that we have in our system. But there is one component, there is one column that is a component column that is going to pinpoint very easily why the prediction fail. If we are tracking PCR, for example, tracking PCR4, that is the one that relates with the bootloader and the kernel, so everything that is an FEI component. If we don't have a component associated with these PCR4 extensions, this is going to be empty, the component column is going to be empty, and it's telling you that the prediction for this extension didn't succeed. And this is the information that is going to give you the hint, okay, something did go wrong and the kernel was not measured properly, or the initRD is not the one that was expected, and you can debug that in your system, checking some JSON files that contain the hashes to understand if it's a security problem in your system or something wrong during the using of the system. PCR15 is an extra security related with roach looks to device. It's an attack that was described some months ago. Basically, if in a normal process, measure boot is going to be extending and updating the value of different PCR until you reach initRD, and the initRD is going to tell system decrypt setup to open the device. If the policy match with the current status, the TPM is going to unseal the secret key for opening the Lux device, and the boot process is going to continue. But what happens if we replace the disk with a fake device that contains the same UID for the device or the Lux2 container? That means that the initRD is going to think that this is the real device and is going to try to mount that in a situation that all the PCR are clean. That means that an attacker technically can enter the password for this Lux device and can, because the PCR are in a good state, can ask the TPM2 to unencrypt the Lux2 password. To avoid that, there are different solutions. The basic one is don't use TPM2. Use TPM2 plus ping authentication method. But there is another solution that is using TPM2 measure PCR that is going to make an extension at the very end. Once the Lux2 device is open, it's going to be an extension of the volume key of the device into PCR15. And you can have another service that can compare the current value of PCR15 with the one that you calculate. This new service is measure PCR generator. It's a bit more complicated, more convoluted, but it's a way to, like the last step, that is not going to deliver any, so it's not going to deliver the process to the new init process inside the Lux2 device if we can guarantee that this is the expected device in our system. Measure PCR prediction can also be debugged. So basically, you need to check that the same keep setup in the initRD is the one that you have in your host. So there is a way to debug that. If you are unsure, you can create a bug process and a bug in Bootloader, and we can work together to figure out why there is a complaint in your system. But the other part is the bootloader specification. This is the other part of sdbootutil. We can manage all the bootloader configuration using sdbootutil. We can update the bootloader. We can check what kind of bootloader we are using. We can validate if the bootloader is working or not. If the bootloader requires an update, and we can force an update or force a downgrade in the system. The same for the kernel. There are ways of adding and removing kernel in our system. Sometimes it's about creating a new entry, so installing from the initRD, installing the kernel in the ESP, and creating a new boot entry for it. We can list and show the entries. We can garbage collect the kind of unused boot entries and kernels that we have in the ESP to recollect more free space. And we can make orthogonal change in the kernel command line for all the boot entities that we have in our system. We can also set the default and timeout so the default boot entry for the next boot and the expected timeout before the default one is going to be selected. And we have more query ways of listing the total kernels that are installed in our systems, snapshots, and devices that are tracked by sdbootutil. But not everything, I mean, by default is going to be transparent, so we really don't need the BLS tooling because transactional update and Snapper are going to inject those plugins that are going to make those chains transparent for us. But sometimes we need to access to the low-level applications. There are more things to work on in the future. Basically, this fixing the firmware update integration, there are ways to doing that. We want to have more authentication methods beside the TPM. We want to have the TPM plus FIDO2. So instead of entering a password, we want to use the YubiKey. So if the system is in a healthy state and the FIDO key is the correct one, now the process is going to boot. More small change. For example, better debugging output while the password is asking during the boot process. Documentation in the openSUSE wiki is updated, so this is a good reference for us. Check that, and if something is missing, ask. So if there is any question. Okay, maybe too fast, no? Yeah, I mean, the documentation is there, so take the idea that we have a different way of doing full disk encryption today. This way is available for us, it's in Just. There is no excuse not to using that in new installation. Play with it and start doing bug reports because this is a very nice way of securing our system.
I have two usability questions. If I do a new installation of this, will I be able to use, I will not be able to use firmware updater, right? Or did I misunderstand?
No, you can use firmware updated, I use that. The thing is that sometimes, depending of your system, sometimes the LUX2 is going to be asked, the LUX2 password is going to be asked. It's a matter of entering the password, calling update predictions, and next time no password is going to be asked. But this is not ideal. So the solution is that somehow an update in the firmware is going to be communicated to sdbootutil, some plugin, some mechanism that is going to calculate the new value of the firmware for you without asking the password anymore.
And the second question is, can I have separate partitions with the same pin and have the tool ask once instead for each partition?
Yeah, I mean, ideally, for example, in my system, swap and the root file system and sometimes bar or etc. are sharing the same TPM and are sharing the same LUX2 key. So I don't need to do anything. So updating the new policy is entering the recovery pin in some situation that is in the TPM, so it's one single recovery pin, and everything gets updated because I'm using the same policy. And when I need to enter the LUX2 key, I only enter one time because system D is going to cache the password, and it's going to try to use the same password for all the LUX2 device. Because it's the same password, the swap and etc. and bar is going to be open. So yes, you can use the same concept, and everything is going to be opening, entering only one secret.
Thanks.
Okay, one last question.
Very quick, for laptop users, you recommend TPM2 plus pin, right? Because otherwise, if the device is stolen, it doesn't make sense.
TPM2 is for unattended servers. TPM plus pin is for desktop, yes.
Very last question.
Okay, for notebook users, would it maybe make more sense to enable the lock screen and use the PAM protections instead of the TPM PIN?
I don't see the relation. The lock screen thingy?
Yes, so when you rely solely on the TPM, for example, on a notebook, the system will boot, but when you're thrown to the login screen, you still can't do anything useful with the device.
I don't understand the relation, basically because what you are protecting is the secret that is going to open the LUX2 device. When you left the laptop, you need to enter a password, but this is the password for the user, not for the system. So it's kind of different. And this password is not going to unlock anything, so nothing is going to be unlocked. Except the screen protector, but there is no device that is going to be unlocked, there is no chipset that is going to be called. So it's a different use case. You are protecting different elements.
Okay.
Okay, thank you.